So this is Collective Effects and Crises in Socio-Economic Systems 3. Sorry to build in there, telling you about more or less the same story over and over again with different, slightly different takes and angles. So there's this. I spoke about exogenous versus endogenous fluctuations in stock markets, but there's also similar debate about the nature of macroeconomic fluctuations. So there's this so-called small shock, large business cycle puzzle, which is associated to Ben Bernanke, the ex chair of the Fed. And essentially, I mean, if you look at the graph that's here, I do with the stick. This is GDP growth in the US since 1950 or something, and you see that year on year it fluctuates a lot. I mean, it's on average it's around 3% per year growth, which is not bad, but the standard deviation is 2.5%. So there's huge fluctuations, and many of these fluctuations are not obviously related to something big happening. Yes?
Is it real or normal growth?
I guess this is real. But check it out. I think that in terms of this number is important. In terms of fluctuations, it doesn't really make sense. So the point is that many of these peaks and troughs, you cannot relate them to something special. So of course, 2008 is the subprime crisis, but you can already discuss whether this is an exogenous crisis or an endogenous crisis. And then, of course, 2020, which is just after that point, is COVID, and there clearly it's exogenous. But in many cases, it's not clear what's the cause of these huge fluctuations. So that's why it's called a small shocks, large business cycle puzzle. And then I'm quoting here, for example, Cochrane, who's an economist who wrote in 1994, what shocks are responsible for economic fluctuations, despite at least 200 years in which economists have observed fluctuations in economic activity, we are still not sure. I think it's a little scary, but anyway. And then I was mentioning this earlier, the European Central Bank at the time was headed by Trichet at the time of the 2008 crisis. And he wrote this, I was actually in Frankfurt. I was lucky enough to be in the conference where he gave the speech, and he said the FG models, classical models of central banks, failed to predict the crisis and seemed incapable of explaining what was happening. In the face of the crisis, we felt abandoned by conventional tools. So I think the fact that it failed to predict the crisis is something, but maybe you can argue that this is difficult. But I think that's really puzzling and worrying is seemed incapable of explaining what was happening. And I think that, when we look back at the last 2 or 3 years of inflation, there's again the problem that the models of central banks were very bad at explaining what was going on. And so central bankers started saying that inflation was temporary, and was nothing needed to contain it, but then they changed their mind, and people are debating a lot right now about what are these models worth in terms of the latest bouts of inflation, and how these models allow us to explain the world. And so again, coming back to the philosophical questions we had earlier, I think models are there to sharpen your intuition about phenomena more than giving you precise numbers. And when they're blind to such enormous things, there's a problem. So that's what I said here. Standard DSG are ill-equipped to deal with endogenous crises, because in these models, the only thing that can happen are exogenous shocks driving the system away from equilibrium. But there's nothing endogenous that can ever happen. The only thing that the system can do, we had that discussion earlier, is to revert back to equilibrium. Yes?
And also, the models are always assumed to be stable.
Yeah, sure. They're linearized around some stable equilibrium. So And actually it was funny to see some predictions of future inflation in the last few years, where every month the inflation was predicted to revert back to 2%, which is the target of central bank, and every month inflation was still going up. And so you can see this sequence of predictions that are curves that always go down, and the actual always goes up. So anyway. So I talked about excess volatility in financial markets. This number that stock valuation fluctuate by plus or minus 2% per day, even when nothing much happens in the world. And I very quickly alluded to models that allow to include feedback loops. And these models always give a decomposition of volatility into endogenous and exogenous that is hugely in favor of endogenous. So there's like more than 80% of volatility in the calibration of these models that is associated with endogenous feedback loops rather than exogenous shocks. And then we discussed a lot this morning about the fact that it's the same story in a sense, but that a lot of the jumps, price jumps, happen without news. Okay, so maybe I don't need to cite Fama. We spoke about Fama earlier, but he's a proponent of efficient markets. He said, well, in 2008, markets reacted immediately to Lehman crisis, and they started to decline in advance of what people recognized that there was a recession. This is exactly what you expect if markets were efficient. So I think it's a very interesting quote because it means that he's completely reverting the cause and the effect. It's saying it's not because of the financial crisis that there was an economic crisis. It was because people anticipated the economic crisis that there was a financial crisis, which I think is I think he got a Nobel Prize in the head. Okay, so going back to the excess volatility, the so-called business cycles. So these fluctuations go under the name of, it's the same brand, go under the name of business cycles. And so essentially the argument that this is large comes from the fact that there's a kind of central limit theorem argument behind this. That is that if you assume that US is a large economy with a lot of idiosyncratic firms that each have their idiosyncratic shocks, then these shocks should average out. And very roughly speaking, the volatility should go down as one of the square root of the size of the economy. And so if you think of the US economy as tens of millions of firms, having 2.5% fluctuations of the GDP year on year is just crazy. You shouldn't get that by averaging idiosyncratic shocks. So behind this excess volatility puzzle, there is this idea that shocks should average out. So how do you escape from this? Well, one way is to say, well, there are actually macroeconomic shocks, but we don't know what they are. But somehow the market as a whole knows what they are, but it's unknown to the economists. So actually, I remember in 2008, seeing a lot of these crazy hypotheses about prices being due to something deep, but that we poor economists couldn't know. So I think it's a very defeatist point of view.
What we do is,
Even nihilist point.
It's a living proof of God exists.
Right.
but we do this in astronomy also a lot.
In astronomy, you mean
Black energy, you can see it, but we use it to come up with some theory.
But until we find something better, right?
Yeah. So,
but okay. I mean, this is a puzzle. So another line of thought is something that we've alluded to yesterday, is this idea that if you have a distribution of firms that is fat-tailed, then you might escape the central limit theorem. And intuitively, it's clear that if the Hafindel index, for example, doesn't go to zero, it means that the whole economy is dominated actually by a few firms, and therefore you don't have this averaging of idiosyncratic shocks because firms, big firms, and it's true that in some cases this exists. I mean, Nokia in Finland, or recently there's the story of the pharmaceutical company in Denmark that explains, I don't remember, 20% of the GDP or something like that. So yes, this exists, but actually when you look at numbers, it's really not strong enough to explain what's going on. And plus, what you see is that these, I mean, even without doing any econometric tests, you see that there's something that happens during these fluctuations, is that different sectors tend to fluctuate in sync. So it's not that one big firm goes haywire, it's really that many sectors move together. And so it's not the question of not averaging out idiosyncratic shocks because of outsized firms. It's really that there are correlation between these fluctuations. And so then people started looking at network effects, because then if firms are somehow connected to one another, and they're connected through input, output, supply chains, then it's much clearer how there can be contagion effects. And so I'm going to speak about this, about, as soon as you have contagions, you can have fluctuation transmitted from one sector to another, and then these kind of synchronization which increase overall volatility. Then, and maybe related to this, although it was framed in a very different language, there's the idea that back in physics, introduced in the late 80s, beginning of the 90s, of self-organized physicality. That is, that complex systems in some cases, not always, but in many cases, they tend to self-organize at the vicinity of a critical point. And we know that critical points develop excess fluctuations. So, in a pictorial way, systems are driven towards a point where they're unstable. And because of the proximity of this instability, fluctuations are enhanced. And so this idea was framed in an economic language in this famous but not that famous paper by Bach, Chen, Shainman, and Woodford. So Bach and Chen are two physicists, and Shainman and Woodford two economists, pretty well-known ones, by the way. But the model at the time was very strange, because it was a kind of blunt translation of a Sampai model into an economic language, but it wasn't plausible at all in terms of economic mechanisms. So it's strange, because at the same time it's a very well-cited paper, but there was no real follow-up. This idea that looked like a maybe interesting idea, but not supported by a plausible model, and therefore I don't think that was a major success. And by the way, even Shainman himself has not pursued until very recently this idea of self-organizing. And then, as I'm going to try to show, there's also another avenue, which is not necessarily self-organized physicality, but the fact that economies are maybe intrinsically out of equilibrium, and the fact that they're out of equilibrium leads to phenomena that we know in turbulence. For example, if you look at turbulent flows, there are all sorts of fluctuations of excess volatility. That could be called excess volatility in the language of economics and finance. And so maybe the economy as a whole is very far from this equilibrium paradigm, and develops endogenous fluctuations because of nonlinear feedback loops all over the place. Okay, so let me review the work that's been done on firm networks. So this is an actual representation of the firm network in the US. So these are the three automakers, and then their suppliers. So you see, I mean, this is snapshot. It's a simplified snapshot, but you see the complexity of this network with very connected nodes and complex structure. So some people have claimed that this is a scale-free network. So I don't know if it's really scale-free in the sense that the distribution of degree is parallel, but at least it's very heterogeneous. It's clear that some firms are heavily connected. Automakers, for example, they have thousands of suppliers. But others are less connected and so on. So this is the type of beast that just visually it's not implausible that this is the root cause of correlation between firms and excess fluctuations. But we would like to.
I would have expected to see Boeing in there.
Oh, maybe it's in there. I don't know. I mean,
it's behind that talk in the Center for Quantum Systems. Can I ask who created this?
So this is from a paper. I mean, there are many representations now. I mean, this is a well-known database called FactSet, and we use it as well with Jose Moran. But this is from a paper by Atalay and collaborators, Atalay. That's pretty famous in 2010 NAS or 2011. So as often, just when you have a visual image of things, then it triggers imagination. And so I think that partly because suddenly one is able to get access to the data and plot it, generates intellectual activity. It's strange, but it is the case. So these firm networks, they have a pretty long history. Oh yeah, that's like 2011, and actually GM Golden Price. So the model dates back to, I mean, the initial version of the model dates back to 2003, Long and Plosser. But the real kick comes from a paper by Asimoglu, Cavallo, and collaborators in 2011. So I'll go through that model first and then give you extensions of the model and things that may not be very realistic about this type of model, and then how to go beyond that. Okay, so there's a unique household, this famous legendary proverbial representative household that works and consumes goods. So there are n goods here, labeled I 1 to n. And so firm I produces good I using labor, and it also needs other goods, input goods. And so the kind of workhorse of the theory is what economists call production functions. So this is the amount of good I that can be produced using some amount of labor hours Li and some amount of product J, Qij. So Qij is the amount of product J that firm I uses, and Li is the amount of workers, if you want, that firm I uses. So let me read this for you, but it's a little strange as a production function. At least for me, it's very counterintuitive, but again, it's the workforce of the field. So Zi is called the productivity factor. So given the number of work hours and the number of products that you can use, firms can be more or less productive. So get out more or less stuff from the same input goods. And so actually the whole economy will fluctuate because of the fluctuations of productivity. So I think we'll talk about productivity shocks. So this is the exogenous shock that is going to drive the whole system. So it's a product. So it's a product of work to some power, 1 minus alpha, times the product over all goods of the quantities to some power of Jij times alpha, with the constraint that the sum of all the JIJs is equal to 1, which means that, I mean, there's kind of constant return to scale in the sense that if you multiply all products and all labor by some factor lambda, then yi gets multiplied by the same factor lambda. So of course you could, you could have a decreasing return to scale with an extra parameter, but here I'm assuming that there's a return to scale, so everything is scale invariant. But you see something important is that this production function assumes that things are substitutable in the sense that if you say, imagine that there's a unique good, so Jij is equal to 1, and imagine that alpha is 1/2, and it would be the square root of L times Q. And so if you divide the number of input products by 2, but you multiply the labor by 2, you're still able to produce the same amount. And in a sense, you're able to substitute the goods that you're missing by other goods and keep your production constant. So this is the production function called substitutable because there's a huge amount of substitutability in the system. Yes?
Yeah, I have a question when you said about the constant returns to scale, that the sum of Jij should be 1, but the sum of the share of labor plus the importance of this intermediate input should be 1. Oh, I thought it should be the sum of, but maybe.
Yeah, that's why, because if you imagine you multiply Q by lambda, all Q's by lambda, then this will be lambda to the alpha sum over J of Jij, which is 1, so it's going to be lambda to the alpha.
Oh, it's.
And L you multiply also by lambda, you're going to have lambda to the minus alpha, 1 minus alpha plus alpha, which is lambda.
Yeah, it's right. It's a different notation than I'm used to.
Okay.
Also, substitutability is imperfect, right? I mean, I cannot substitute completely one input from the other because I have 0 of something. So I cannot substitute coal for electricity in that function.
Yeah, okay, so if one of the Q goes to 0, then you're done.
Right, yeah.
But
quantity can be compensated.
But a part of this can still be compensated.
Yeah, so I can have like half many motors, but twice as many seats for my car, and still somehow make it the same amount of car.
Exactly.
By making bigger cars with
Right.
more seats.
But still, there is what you say that if one of the Q is really 0, then you're done.
Right. Okay.
So that's why I said, but why? Because I mean, if you look at the justification of this. There's a paper from the 50s trying to justify this production function. But to me, it's like, okay, we'll go back to that later. So anyway, this is the starting point. So next, one does what economists do. So households maximize their utility. So the amount that they consume of product I is inversely proportional to the price because they have a budget constraint, and theta I is the preference of agents for product I. And then firms, what they do? Well, they do what firms should be doing in standard economics, right? That should maximize their profit. So what is their profit? The profit is production times price minus labor times cost of labor minus what they have to buy, so Qij times the price of product J. Okay. And then there's a very important further assumption, which maybe you should have frowned upon at this stage, is that in theory, the profit is not the production times the price, is what you are able to sell times the price. But here we're going to assume that markets are in equilibrium. So in equilibrium, markets clear. So everything that's produced is instantaneously consumed. And so therefore you can identify yi with the quantity that gets bought, which is CI bought by households plus what's bought by other firms to produce their own stuff.
Price is not correlated with production.
Price are such that markets clear.
Yeah.
and the sum of the labor force is, I mean, the sum of the total labor force must be equal to labor used by time. Okay, so here I've sketched the maths, but maybe I won't go into the details. What is important to note is that these equilibrium equations always have well-defined solutions. That is, if you solve these equilibrium, I mean, these relations that I've talked about, that is, firms maximize their profits in good and labor markets clear, leads to prices and productions that are all positive quantities. Okay, so if you find a negative price or a negative quantity, that's a problem, right? So this is not the case. This is not the case in this version of the model. These equations are well defined. For example, there's a vector here that's the log of prices. So if you've taken the log, then obviously prices are all positive. And then there's an equation, a matrix equation like this that gives you the vector of prices, of log prices, knowing this input-output matrix and the coefficient alpha, which is, you remember, the share of labor in or the share, well, 1 minus alpha is the share of labor that can be interpreted within this model as the share of labor in GDP, and it's estimated to be around 1/3. So 2/3 of GDP comes from labor. There's also a similar matrix equations for sales, so the total sales of the firms, which again has a random walk interpretation, and this ensures that the solution is always positive. So you can, there's a random walk interpretation that your sales are given by what the households want to consume plus what the firms around you needs to consume, but then there's an infinite series of that you need to solve in order to get the sales. So this, as I said, this has a random walk interpretation in terms of density of random walkers. And so from the interpretation, you know that S is always a positive vector. So P is a positive vector, S is a positive vector, so everything's fine. So you have a well-defined solution. For all productivities, prices and production are non-negative. Okay, so how do you go from there? So maybe you recognize this slide from yesterday. So the variance of the GDP, so where does the variance of the GDP come from? It comes from the fluctuations of ZIs, as I said. So you assume, so in this model, that's what I would write here, fluctuations are totally induced by productivity shocks. So at time t, Z is a vector, it has some values. And then at time t plus 1, all these Z's fluctuate by some amount. And you assume that immediately a new equilibrium is reached. So there's no transient. Or immediately firms know what to do, they change their prices, everything comes to roost nicely, and up. There's a new equilibrium with new prices, new productions. And so these are the sales, the new sales. And what you can show is that the variance induced by these fluctuations of productivity translate into the variance of the whole economy through this factor, which is exactly the Huffindel index of the economy. So this is the sum from I to n of the sales squared, 1 over n squared. And so now you recognize this, what I said at the beginning, the fact that economists have in their heads have this 1 over square root of n paradigm, because this is exactly what you find from this model. You find that if the size of firms measured in terms of sales is well distributed in the sense that the distribution of sales is a power law with an index that's greater than 2, then the half-interval index goes as 1 over n. So the variance of the GDP goes as 1 over n. So the mean square of the GDP goes as 1 over square root of n. So this is a complicated way of stating what I said initially of the central limit theorem, but it comes out in the model. And then this is what Gabet is saying is that, well, actually we have firms that are marginally that have very broad distribution of sizes, and so we are probably not in that regime, but close to that regime. And in this case, volatility does not decrease with the size of the economy. Okay, so this is nice, and so in a sense it explains at the same time the standard argument and Gabet's argument. But you see that there's something that seems to be missing, at least for me, which is that although we stated initially that networks were probably a great tool to introduce contagion effects and propagation of fluctuations and so on, there doesn't seem to be any of this because there's equilibrium at each instant of time. So where is the disturbance propagating? We assume that all the internal dynamics of the system is so fast that it has equilibrated, and we're never in an out of equilibrium regime, which may explain also some part of the fluctuations. So this part here comes from Jose Moran's thesis, and we were asking ourselves, well, can we extend this model so that we might have a richer framework where something more radical can exist, like firm bankruptcies and real problems that propagate in a way that is maybe more faithful to the initial motivation of using these networks as a source of excess volatility. So I'm going to tell you the story, and at the end of the story, we find something that actually resembles a lot this back Schenkman Woodford scenario of self-organized locality. Okay, so let's now look at a different type of production function. So this is the so-called constant elasticity of substitution, CES, production function. So again, maybe my notations will not be the same as the ones you know, but so essentially now I'm going not to distinguish labor from the rest. So labor is just index 0 in that expression, and QI0 is what I call Li. So this looks barbaric. So there's an index Q here. There's still the ZI, which is the productivity of the firm. And then there are inputs, JIJs, and this new coefficient JIJs and so on. So let's try to see what that means. So it turns out that this is a family that in some limit, in the limit, mathematical limit, when you take Q to infinity, then you recover exactly the cup-to-glass production function that I talked about, this product of quantities. But in another limit, Q equals 0, you get something that to me is very physical somehow, which is called the Leontief production function, which means that what you're able to produce is not the product, but the min over J of some ratios here. So Qij here can be interpreted as a kind of, I mean, if we were chemists, we would speak about stoichiometric coefficients. So, sorry, the J's, the Q's are quantities. So if you want, you spoke about cars earlier. So if J is tires, then Jij is 4 because you need 4 tires to build a car. And if you don't have 4 tires, then when you're done, you can't build even a single car. Okay? So this means that you're constrained by the rarest product that you have, and you can't substitute. This is really the case where you can't substitute at all. So Q is a kind of index of substitutability. Q equals 0, no substitutability whatsoever. Q equals infinity, some level of substitutability. You can actually choose Q negative as well. So what we started doing with Jose was to look at the same model, but in this extended framework. And at the beginning, the first version of our paper was about Leontief, and then we sent it to Xavier Gavex, who said, "Oh, but Leontief is very special, so maybe what you get is because you studied Leontief." But what we realized then is that actually it's the other way around. Is that in this family of production function, which again I don't know exactly where they come from, and they look very strange to me, except the Leontief one. But it turns out that the Leontief is the generic case, and the Cobb-Douglas is the special case. So for any Q that's not infinite, what I'm going to tell you is true. And only when Q is infinite, you remove the problem that I'm going to talk about. So that's interesting because it means that what I'm going to tell you is more generic than the Cobb-Douglas. So, but let's look at the Leontief limit, and as I said, it's going to be generic, although the equations look uglier. So, what you get for the price and for the production, gamma is essentially a measure of production, are two linear equations that resemble what we had before, but they are different. And in particular, here instead of having log price, it's price, and G is this coefficient of stoichiometric objects. And so, formally, you can always, provided this matrix is invertible, you can write P equals K is a positive vector in the sense that all its components are positive and C as well. So in principle, you can write P equals inverse of this applied to K, and production equals inverse of this, which is a transpose of this applied to C. But the problem is that nothing tells you that the solution will be acceptable, in the sense that it's not because the matrix is positive that its inverse is positive. So there's a criterion, which is called the Hawkins-Simon criterion, which is that this pair of equations only has acceptable solutions in the sense that all prices and quantities are positive if this matrix Z identity minus G is the so-called M matrix that has various equivalent ways of stating the condition, but essentially, if these equations have to have only positive solutions, then the eigenvalue with the smallest real part of this matrix has to be positive. I mean, the real part of the smallest eigenvalue has to be positive. This is a necessary and sufficient condition such that the inverse of this matrix applied to a positive vector gives you positive quantities. So there's a constraint, and in particular, it's going to constrain the input-output network, which is G, and the productivity vector, which is Z. So I'm going to give you examples of that. But before doing this, what's interesting and what we noticed at the time is that these equations and their solution are formally identical to the equations that determine the number of species of different, the population of different species in a Lotka-Volterra equilibrium. So for those who don't know this Lotka-Volterra or generalized Lotka-Volterra framework, Ni is the number of individuals in species I, and its evolution is proportional to the population itself, times the term Fi, which is interpreted as a fitness, so fitter species grow faster. Then there's the saturation term, And then there's a term describing interactions with other species that can be competitive or cooperative, depending on the sign of each phase. And so if you want to solve for equilibrium, then of course the Ni dt must be 0. So either Ni is 0, species is dead, or for species that are alive, this equation has to be obeyed, right? Z minus G equals F. Z minus G applied to M equal F. But of course, we're speaking about populations here, population of species. So it would make no sense if N was negative, or had negative number of cats or rabbits. So what it means is that in a complex ecology, you have generically, you have to kill enough species such that the resulting equation here has positive solutions. Otherwise, you're not finding an equilibrium. So by the way, I mean, as you know, this for two species is the famous rabbit and fox model where populations are evolving. So if you're, of course, you can have dynamical solutions to these equations which are not stable, which are not stationary, where the Ni dt still evolves with time, like in this example. But if you impose that you're looking for a stationary solution, then generically you have to you require that some species have to go extinct. And it turns out that in many cases, you can show that what is going to happen is you're going to decimate enough species such that the Hawking-Simon condition is just marginally satisfied, which means that you're going to stop decimating exactly at the point where the system is unstable. And this is really what Robert May was arguing in his paper. With a complex system be stable, he was saying that if you have a complex ecology, if the number of species gets too large, then the system is generically unstable. And what he was kind of hinting at was that therefore you had to get rid of some species to get back again at stability. And it turns out in these log-Cavalcera models that in many cases you stop exactly precisely at the point where there's enough species, well, not too many species such that these equations can be satisfied with positive entries. So in other words, when this matrix Zi minus G has a zero eigenvalue. So in order to have a little intuition about the Hawking-Simon condition, let's look at a simple case where each firm has exactly C clients and C suppliers, randomly chosen among a very large number. So this is called random regular network. It's random because the clients and suppliers are chosen randomly, but it's regular in the sense that there's a fixed number of clients and suppliers for each firm. So of course, it's a very simplified framework. But it's interesting in the sense that in this case, everything can be solved analytically. And so what you find is that in this case, the eigenvalues of M, what I call M before, this object here, it can be computed completely, and the eigenvalues are as follows. There's a kind of isolated eigenvalue, lambda min, which is real, and it's the closest to 0, which is equal to productivity. So here I've assumed also that productivities are all equal to the same Z, minus connectivity times stoichiometric coefficient, number of products that you need to have. So here again, if Jij is non-zero, it's all equal to J. So you need the same amount of each product. So it's a super simplified model, of course. but it gives you a hint of what you should expect of these matrices. So there's this one that's closest to 0, so that's the one that's going to determine the stability of the system. And then there's a whole bunch of eigenvalues within a circle in the complex plane centered around Z with radius R, which is G square root of C. So this is the circle of eigenvalues in the complex plane, and then there's an isolated one that's here. So here is actually the spectrum of -m. So this one is on the other side, but you should think of it as flipped over. So what you see clearly is that the economy is only functional when Z minus CG is positive, that is, if productivity is high enough, or if the number of goods that you need is small enough. Otherwise, you can't find a solution where all firms survive. So that's what I said here. The economy becomes unstable when productivity falls below some threshold, which if you drop this assumption that all Jij's is equal to G, it's just the expected value of G and not its value. Okay. So if there's high conductivity or strong needs of good, then you will destabilize the economy. Okay, so this is of course a very simple model that is completely unrealistic. So we studied the case where productivities, instead of all being the same, are randomly distributed in a certain interval. And then this graph represents the eigenvalues, the real part of the eigenvalues of this M matrix. So okay, I'm not going to go into the details here, but tell you what you learn from this. So at this point, it's very tempting to say, well, this gives us a way to reinterpret the self-organized scenario, a criticality scenario of this paper that I've cited already. You see aggregated fluctuations from independent sectoral shocks, self-organized criticality in a model of production and inventory dynamics. So I think the title is a little misleading, because then when you look at the model, you don't recognize at all sectors and inventory dynamics. It feels very, very remote from what they say, but at least the ideas are there. And within the framework of this network model, it's very clear what it means. It means that as you look at your system, there are many ways that are, in a sense, natural, by which you will drive the system into the critical point, where, as I said, the criticality is determined by the smallest eigenvalue of this matrix, and when it touches 0, then you have to kill some firms in order to revive the economy, I mean, to have an economy that's functioning. And so these, I've listed here the scenarios by which you drive the system at the critical point. So one of them is just if you keep everything the same, but you grow the network. If you have everything else being the same, if you add more firms in the network, at one point, you'll reach this instability point. And so this is really related to May's instability, the May instability of ecologies. Another way is to think that the average connectivity of the network increases. So you can think of that as a kind of complexification of the supply chain. That if firms need more and more different products to build what they need to build, then at one point you'll reach this instability if productivity is kept constant. So when you think about, again, number of items you need to build an iPhone or a car, probably it has something to it that, you know, as a function of time, we're making more complex objects, and therefore the networks get more and more connected. So as I said, I mean, although I've shown you the math for Q equals 0, actually the same instability is present for any value of Q except Q equal infinity. And therefore, if you start with a value of Q that's high enough, all parameters being fixed, then you can be in a stable phase, but then as you reduce Q from the initial value, which means that you make goods less substitutable or less redundant, so it means that firms try to have lean supply chains and cut links, because it's costly to keep links that you're not using, so maybe you want to have as little suppliers as possible, but this will drive through this parameter Q at one point the system to this marginal point. And then there's something else that I didn't speak about, but you can include in the model margin costs. So if firms want to make profits and they increase their margin costs, then everything else being the same, again at one point there will be will hit a snag and the system will become unstable. So if you look at the list of these things, it's not obvious, of course, but it's at least plausible in the way these people argued back then that economies spontaneously through evolution kind of hover around the point where they would be unstable. And then if they're close to instability, we recover this idea that any small shocks will be amplified by the proximity of this instability. Yes?
Yeah, so when you talk about instability, I mean, did they ever make a time series or something where they map what the instability means? So does it mean business cycles, or does it mean that the economy will fully collapse? Or do they just look at, okay, we reached this magical point, there's some eigenvalue, there's some crazy things, but we don't really look at what actually like happens in the
You mean in this model here?
or some follow-up paper?
No, I mean, as I said, I mean, there was very little follow-up paper until we tried to revive this, and
if
I
it
think
was you, that's also interesting. I mean,
yeah. So let me go through what I think next, and maybe then we can discuss about empirical facts. Yes.
There's one question around Q, more or less substitutable. In an economy where we now face shortages of metals and other things, does that mean a shrinking Q, or is that not the same? So we've lived in a time where we thought, capital was limited and the resources we needed for production were unlimited, like metals, for example. We're now coming to a time where that is no longer true. I was just curious if the Q here reflects that as well. So
well, in the sense that they're not substitutable, yes.
Yeah. So yeah, but because the situation with rabbits and foxes, of course, you have a limited capacity of an island that they're living on.
Oh yeah, I mean, this analogy was just meant to be at the mathematical level.
No, I know, but the reason
at this point,
yeah.
This model is a dynamical model.
Yeah.
Whereas, as I've emphasized, the network firm model is actually a static model.
Sorry,
everything is static.
I didn't know.
That's what I'm going to argue next. I mean, here again, the logic is again, at this point, I've just changed the productivity function, but I haven't changed the assumption that markets clear and that firms optimize their profit. It's the same logic. And so here again, except the fact that now you have a stringent condition on the feasibility of the equilibrium, the viability of the equilibrium. Apart from that, the assumption is still the same, that there's a value of productivity, Z, you compute equilibrium, you go to the next step. And the next step will be immediately equilibrium. So there's no dynamics. And that's what I want to move to next. So this is not an answer to your question about data, but at least within the model, what we find is that if you're close, again, if firms have sufficiently heterogeneous productivities, and you're close to this instability point, then you can study avalanches in the sense that, when one firm goes bankrupt, how many firms go bankrupt with it? And what you find is these nice power laws that I talked about this morning. So in a sense, we're in the situation that Bach et al. Were arguing for, that these becomes very similar to mass extinction in ecologies, and so it's the fact that you have all these fat tail distributions is a way to amplify fluctuations compared to what happens in the Cobb-Douglas case. And there's an interesting phenomenology that could explain crisis and so on, which again doesn't exist. I mean, here you see that there's a need of bankruptcies, whereas in the Cobb-Douglas production case, since there's always a solution, no firms ever become bankrupt. But still, as I just said, I mean, here you've assumed that what physicists would call adiabatic, that is, that equilibrium is reached much faster than any other process. So there's a change of productivity, but then immediately equilibrium is reached. And so this is not satisfying. We need to understand what's going on if we don't make this assumption. And by the way, because the system does not necessarily have an equilibrium, what happens in this model where lambda min is less than 0? That is, okay, we know that equilibrium is not feasible, but so what happens? And if you don't have a dynamical extension, you can't even answer it. So clearly, if you move beyond the Cobb-Douglas case, you absolutely need to think about equilibrium, about dynamical dynamics, and the fact that you don't reach equilibrium instantaneously. So we try to build models for non-equilibrium dynamics within this network model. And so the first idea we had was to write kind of what physicists call phenomenological equations and what economists call reduced form equations that tell you what is the dynamics of prices and production. Since we want to have something that's out of equilibrium, we need to write actual dynamical equations that could lead to 0 in equilibrium, but that in more general leads to something non-trivial. And so, okay, equilibrium means that production is equal to consumption, and that profits are equal to their equilibrium value, which turns out to be 0 in this model. So it's natural to think, well, then if I'm out of equilibrium, it means that there's either excess production or excess consumption, or that there's excess profits, or actually losses. And then firms will react to these excesses or excess production or excess demand by adapting their prices and their production. So maybe you don't need to read in detail this thing, but we try to convey simple rules that for example, if firms overproduce, then they'll be tempted to reduce their production next time around and reduce their prices to sell more. So this is essentially what these equations try to encapsulate through these coefficients A, B, B prime that are left as parameters of the dynamics. Okay. So that's what I wrote here. In equilibrium, there's no imbalance between supply and demand, and there's no excess profits. But out of equilibrium, these equations are meant to try to give a framework for how they wash away with time. So that's the first thing we started doing. And then what is nice is that what you find following that route is if you call U, so there's an equilibrium of prices and production, and so U is the deviation from prices, from equilibrium prices and equilibrium production. So if you have n firms, dp is an n-dimensional vector, and dy is an n-dimensional vector. So U is a 2n-dimensional vector, and what you find, because you see here we've assumed everything is linear in these quantities, that you will find a linear stability equation. So in a sense, this is what you would like from a kind of econometric approach or general approach, that the evolution of the perturbation away from equilibrium are proportional, I mean proportional in the sense of a matrix, to these deviations. And then there's these famous exogenous shocks that play roles. And what turns out to be the case, which again was not something that we expected necessarily at first, is that the smallest eigenvalue of this matrix is proportional to the smallest eigenvalue of this matrix n that I talked about, so the famous lambda min. So why is that important? Because you see that if you go to the space where d is diagonal, the eigenvalues of d are going to give you the rates at which these perturbations decay with time. And so the larger lambda, the faster these deviations decay, and the smaller lambda, the slower these perturbations decay. And actually, if lambda min goes negative, then actually perturbations, instead of regressing, become unstable. So what we thought was interesting about this model was that we found the same criterion as the Hawkins-Simons criterion for the dynamics as for the statics. Maybe not completely surprising, but more precisely, lambda min can now be interpreted as the inverse of the relaxation time of the system. So if you believe in this self-organized critical scenario, when lambda min is small, it means that the relaxation time is large. But if the relaxation time is large, suddenly you cannot neglect dynamics because you won't reach equilibrium instantaneously. So that's the first point, that kind of in a self-consistent manner, you find that if the system is close to an instability, you actually cannot think of this system as adiabatic. You cannot absolutely think that it's always close to equilibrium. On the contrary, dynamics will, out of equilibrium, dynamics will completely dominate the dynamics and not the adiabatic, smooth change of productivity that is used. So that's the first point. And the second point is that we find that the variance of U, so you can, from this equation here, you can compute the variance of the fluctuations, and what you find is that it's equal to the variance of the exogenous shocks multiplied by this factor 1 over lambda min. So it's the same thing. At the same time, dynamics slows down and fluctuations explode. And so that's a very interesting mechanism, I think, is that this small shocks, large business cycle puzzle that I talked about at the beginning, in this case, it's really completely explicit. You have shocks of a given variance that is small, but through the network, the variance gets amplified by the proximity of an instability point. So for me, it's really a precise incarnation of the self-organized critical scenario of back-down. So we're quite happy with this until we realize that actually this model has a lot of problems if you want to think about what it means at a kind of micro level. So at the micro level, clearly if you want to build a model for the dynamics, you should move to a more kind of agent-based model where you think about how things, a timeline for which things happen in the model and in reality. So for example, obviously you have to respect causality. That is, firms have to produce what they want to produce, but they don't know what consumers will end up buying. So there must be a causality, a chain between production at time t, consumption at t+1 with what's being produced. And if farmers overproduce, well, then too bad, or they underproduce, then too bad. Maybe they have to adjust, but if farms didn't produce enough, for example, then consumption cannot be larger than production. So you cannot. There are bounds, there are constraints that cannot be violated. Also, that's what I said here. Consumptions cannot exceed production. Then, in the other way around, if farms overproduce, then there will be inventories. So, in this, as soon as you go away from market clearing, you realize that there's a lot of problems that you need to cope with. And I think that's one of the reasons people avoid going away from market clearing, because then you have to think about a lot of things that don't happen when you have market clearing. For example, what happens with surpluses, inventories, and so on. But obviously inventories are important in the real world. So as soon as you go away from this, then you have to say things about inventories, the way they perish, if they're perishable products and so on. So in the end, the dynamics that we came up with that respects these physical constraints is much more complicated than that one. And then we move to the realm of agent-based models, where we make already at this stage we kind of postulate these rules, but we need even to postulate even more rules, like, you know, what do you do with inventories, how do they decay with time, and so on. So we build that more extended model that I'm skipping and not giving you the. You can look at the paper, by the way. So this is a paper with Théo Dessertaines that was published in the GEDC in 2020. So we try to carefully build this model with all constraints being satisfied, and to our surprise, we found something I think quite interesting, which is well, one way to describe the results is through this phase diagram. So this is the strength of the restoring force in the face of imbalances. So if you want, this is the equivalent of these coefficients here. So how much firms react to imbalances? How strongly firms react to imbalances? Here they react very, very weakly. Here they overreact to, or overreact. They react very strongly to imbalances. And in this axis here is the perishability of products. So if 0, it means that products are stable forever. If 1, it means that they, as soon as the next time step is reached, they are stale and you have to throw them away. So there are other parameters in the model, but we thought that this cut in parameter space was one of the most interesting. And what you find is that there are various regions. One where here the economy is completely unstable, goes berserk. Here there is, well, first of all, let me tell you that everywhere we are in a case where parameters are such that the equilibrium is well defined. So the open-Simon condition, or the equivalent of the open-Simon condition, is obeyed. So in principle, there is a well-defined equilibrium everywhere in this phase diagram. And it's the same. These parameters don't affect the equilibrium. So it exists. But the problem is that here the dynamics goes completely berserk. Here you converge to equilibrium, to the general equilibrium that economists like, if you want. And so this is an example where you give an impulse to prices, and then it relaxes to the equilibrium price that you expect. So this is the phase where, if the world was such that everybody agreed to use these parameters, then maybe we would be in a safe place. But then there is this region where either perishability is too small, so there's a lot of inventories that stick around, or firms start overreacting. So as soon as they have overproduced a little bit, they try to reduce full steam and vice versa. Then you generate endogenous cycles. That is, here there's no exogenous shock at all, but the system never equilibrates and enters a whole lot of interesting ways to get away from equilibrium. For example, this is a case where you have cycles, and actually this is a case where all firms cycle together at the same pace, I mean with the same phase, but there's another possibility where all firms oscillate but with different phases, and there's also much more complicated dynamics like this kind of chaotic dynamics where firms are in sync but no clear periodic patterns. And again, all this is without any external shock. So if you want, this is really excess volatility to the extreme, because excess volatility usually means there's fundamental volatility and then it gets amplified. Here, the fundamental volatility is zero. There's nothing at all in the model that evolves with time. But the dynamics, the endogenous dynamics of the system prevents it from reaching equilibrium ever. And then I mean, what's interesting is that although the model is kind of complicated, it's not that complicated either, and you get a full zoology of different scenarios. So for example, there are also these strange regions at the boundary between cycles and chaos and stability, where the system looks stable for a long while, and then there are endogenous spikes where suddenly it gets completely unstable and restabilizes later. So I think this is all very interesting, except that we're now faced with another scenario for excess volatility. Because here, we're very far from the Hawking-Simons instability or the self-organized critical scenario that I talked about. Here, the system, in this phase, it's completely stable. Lambda min, if you remember my lambda min, we chose in this phase, this lambda min to be staunchly positive. So there's no incipient instability in the system. It's just that through the sheer existence of these non-coordinated dynamics, the system is just unable to find its way to equilibrium. And so we have another possible scenario for solving the small short large business paradox. It's a kind of spontaneous turbulence scenario. It's not an instability scenario. And so to come back to your question earlier about empirical data, when we discovered that, we thought, okay, well, we have to think a little more, because now it's not that we want to test the self-organized criticality scenario. We want to test whether we're closer to this self-organized thing or to a kind of endogenous dynamics. Yes?
Yeah, could a bit of clarification?
Sure.
Yeah, because the x-axis said strength of restoring forces.
Yes.
But maybe it's a stupid question, but restoring forces from what?
From
So
imbalances.
Okay, so but that's then industry specific.
Here it's the same for all firms. We assume that all firms have the same strategy to restore imbalances.
But you do take into account this network.
Oh yeah, sure.
Yes,
Of course. Yeah, of course. I mean, it's the same model as before. So there's input, output, firms that need products from elsewhere and so on. And therefore they can compute their target production and target prices from equilibrium. So there is an equilibrium value for all these things. But then at a given time, they observe that they are not in equilibrium, because
so that's the
they try to be in equilibrium, but they observe that they will overproduce or underproduce, or that they make excess profits or they make losses.
Yeah.
And they react to these two signals, excess production and excess profits. So these are these two terms here. And the strength of restoring force are these coefficients here.
How do you measure perishability then?
Perishability is another parameter.
Yeah, okay. Maybe I should ask, yeah. because-
Perishability is there's a decay rate of the product. So for
Yeah.
example, if you sell apples, then probably it's 1
No,
week.
makes
And
sense. But you don't use data for it, you just model.
no. For the moment, this is just this is not calibrated to data. This is just a proof of concept model that tells you that from a kind of methodological point of view, I think it's the first step when you write down a model. It behooves to you to know what the model is going to say about reality before trying to calibrate. And what we try to do first is to know how wide is the phenomenon, the number of phenomena that we can describe within the model. And we were surprised to find so many things can happen within the simple model. And then, if your next step is to try to now go to data and to have a much more complicated model, because of course, when I'm drawing, I mean, in a sense, you are asking a right question, because here I have at least these 4 parameters that might not be the same for all firms. So I have a huge number of parameters. But if I'm not trying to prune down the number of parameters, I won't understand anything about the model. So here, what we've done in this axis, strength of restoring force, is to assume that all these i's, all these coefficients A, B, B prime, A prime, are the same for all firms, and they're actually even the same. All of them are equal to the same value. So this axis here is A equal B equal A prime equal B prime. And so it gives you an idea of what can happen.
No, this now is clarified. Okay, thanks.
Yes?
I have a completely different question about
Sure.
the same system of equations, because it reminds me of Hamiltonian equations of dynamics.
Well, the
Have you-
problem is that they're not.
Okay, good. You have thought about it.
Yes, sure. So for example, there's no obvious conservation rule. And that's why, by the way, you can get such variety of behavior. Yeah, it would be great to have some more structure from a mathematical point of view. But, and probably there are cases we didn't try very hard, but probably there are corners of parameters value where equations acquire extra symmetries that allow you to do something. But this investigation was mostly numerical.
My other comment was that the next equation seems like the Hamilton-Jacobi equation, based on
Which one?
the previous slides. One back. Yeah. So has the same form. If the others are Hamiltonian, then this would be the associated Hamilton-Jacobi.
Well, to me, this is just, linear stability analysis. This is, you have a linear, whatever dynamical system, if you make small perturbation around an equilibrium point, you will have this type of structure, and everything is hidden in the structure of D. Okay, so this, as I said, the graph that I've shown you before, you don't see it here, but this is what is called epsilon here is the value that I called lambda min before. So the graph that you've seen before corresponds to lambda min equals 100. So we're very, very far from instability. The system is really, from the point of view of the statics, is completely robust. But still you get this problem. And now we're reducing lambda min, so that's 10, that's 1. So you see that this region here of economic equilibrium is shrunk, and then epsilon equals -5. We're in a place where equilibrium doesn't exist, but the dynamics still make sense. of course, there's no blue region anymore because there's nowhere to be, the equilibrium is nowhere to be found, but you see that, well, there's a what we call deflationary equilibrium here, and then there's a phase of cycle and chaos. But at least the model makes sense, even if equilibrium is absent. But I think the most interesting point is that is the converse. That is, even when equilibrium is present and stable, you get a lot of anomalous dynamics in the system. So something that we are thinking about is here we have not tried to describe what happens. I mean, there's a lot of things missing. For example, firms that get indebted, they should, they at one point they can't get indebted forever. So there should be a mechanism for default, bankruptcy. There should be a mechanism for birth of new funds. Everything is not, I mean, nothing of that kind is done at that point. And also something really important, and I think this is really something that is super interesting and needed is dynamics of rewiring. That is, you see, if we take a production function like Leontief, then we've included something very non-substitutable. But in practice, what people will do when the price of what they need goes too high, or the firm they buy from defaults, well, they're going to rewire. And so here, and coming back to maybe your question, here the dynamics is at the level of prices in production, but there's no dynamics at the level of links. So the network is fixed once and for all. But in practice, of course, the network is going to evolve. And so I think that including in these models an explicit dynamics of rewiring is something that's needed, and some work is starting in that direction also in the economics side. And so we're hoping to do more on that. Yes?
So have you any idea yet how you want to tackle this? Like, do you want to use, for example, preferential attachment, or just
Yes, so we already have actually a paper that is slightly in a different, with a different objective. Let's go back to the Leontief for a second. So this equation here, the Leontief equation, means that you have a prefixed number of suppliers. But actually, what you could do is, beyond this equation, you could say, well, I have a prefixed number of sectors that I need to supply from. And within these sectors, I have a choice between different products. And I'm going to choose one of them. So my technology is actually imposing a structure at the level of sectors.
Yeah.
But within each sector, have a choice to choose one among 10 companies belonging to that sector.
Yeah, and do you think it matters? Because like for my model I'm using, I'm using the same method that you're using, like fixed sectors, that's random choices. But I'm using code of someone else, so this is choice has been made for me. So there are choices being made that the likelihood that a firm is chosen increases when the firm has a lower price or has a larger size, meaning like it's more visible on the market or whatever. Like, do you have like any idea, like?
So what we did in our paper for rewiring is that at each round, firms can change one of their supplier if they get a better deal.
Okay.
So they're going to recompute their expected profit based on the information they have. If they change supplier, and if they do change supplier, they will do it. Yeah. If they improve profits by changing supplier, they will do it.
Yeah.
And then we repeat. And what happens is that as soon as the economy becomes a little large, this rewiring process never stops. So the system actually never converges to a unique network.
Yeah.
Because there are in a huge number of networks that are of similar quality, collectively. And so the system as a whole is actually, through this dynamics, is going to hover around all these possible networks.
Yeah.
And the dynamics is never going to stop.
Yeah.
Okay. So they don't start concentrating towards the, because, you know, I would have thought they were concentrated all around the supplier that is the
You
lowest
didn't have.
cost.
No, because you know, the supplier prices are themselves determined by its own clients that are going to, I mean,
Okay.
it's just because the dynamics becomes so horribly complex that if you
Don't
have a
break
kind
it
of
down.
myopic rule for the dynamics, I mean, only science, what's it called, social planner would be able to compute out of all these factorial n. I mean, it's really combinatorial complexity here. There's a very, very large number of possibilities of wiring. And among all of them, if there's clearly one, I mean, generically, there's one that's better than all the others, but it's marginally better. And so using that one instead of another one doesn't really matter anyway. And finding the true optimal one is an NP-complete problem. So, you know, nobody on earth is able to do that. So it's completely crazy to believe that, you know, firms collectively are able to make this choice. So the only way you can, I think, reasonably model this dynamics is using kind of myopic rules of the type I've said, that each firm individually tries to do the best, and then you see whether this dynamics converges or not. And what you find is that in general, it doesn't converge. It doesn't mean that the system is no good at the global scale, because it hovers around, you know, suitable solutions. I mean, this is really the satisficing concept of Simon. The solutions that are found are not necessarily the best ones, but they're okay. They're good enough.
Then you probably didn't have mergers and bankruptcies and
No.
that.
No, that's what I said. I mean, this is really needed. You know, we need to. So we have other agent-based models where bankruptcies are included, but now we need to do the merge between the agent-based models where we don't have firm networks and the firm networks where we don't have bankruptcies, and try to make a kind of brand new application.
So the Italian authors you mentioned, they have some nice papers that combine both networks and.
I'm not sure.
Well, then Carlsonus and Sebastian Polletta.
Yeah, of course.
They have the
Yes.
42
Yeah, that's
Yeah,
probably
so
the most.
I'm working with their code.
Okay.
That's my supervisor as well.
I see. So you're in contact with Jose, I guess, as well.
Jose?
Moran? Jose
No,
Moran?
I'm not. No.
Oh, you're not. Okay.
No, like I'm also work with Sebastian Polletta.
I see.
There's also the Italian group in Pisa, with the escape model, like Dozy and Proventini.
Yes, yeah.
They have, I mean, I work with their model, they do have stuff like bankruptcy and rewriting, but they only have two sectors.
Yeah. They don't have this full network of firms.
Well, yeah, I mean, yes, they have, but it's only two levels, so they have the machine producers and the
Yeah,
consultant
sure.
producers, and within that, they have all the phenomena you mentioned, but it's a small amount.
Jean-Philippe, I was wondering, in the model you discussed, do you also have switching costs for switching deals?
Yeah. So actually, this is something that when I said that this dynamics of rewiring goes on forever, of course, if you add rewiring costs, it's going to stop at one point, because the marginal improvement of rewiring will be below the cost of rewiring. So that's indeed a possibility. But then you know the network that is going to be generated by this phenomenon is not predictable in a sense. It's completely dominated by history. It's going to stop, and maybe I'm going to just say that in a second. So okay, so the fund network scenario for small short large business cycle. As I said, fund networks with non-substitutable goods, in the sense Q not equal to infinity, become unstable in a whole region of parameters. I've told you about the kind of naive approach, which is just linear dynamics, which has a a lot of problems in terms of compatibility with causality and inventories and all these things, but they show that close to this instability, equilibration times are long, and fluctuations are amplified. And I think the fact that equilibration times are long, this is in any case important. I think that really the model that tries to explain what's going on in the economy cannot sweep that under the rug. I think that the fact that economies are intrinsically out of equilibrium all the time, more or less so, and this has to contribute to fluctuations. I don't see how this can be avoided. And then I showed that actually you can be very far from any instability at all, but still have turbulent economies in the sense of what I've showed. When firms tend to overreact, then there's a breakdown of coordination because firms overreact all the time, and so collectively the system is not able to reach equilibrium, and therefore you have turbulent fluctuations. So on all these points, I like very much this paper by Olivier Blanchard, where he was reflecting on the 2008 crisis, and so he wrote this paper called Where Danger Lurks, and he says, we in the field did think of the economy as roughly linear, constantly subject to different shocks, constantly fluctuating, but naturally returning to equilibrium over time. So he really speaks about these DSG models that I alluded to at the beginning. So it's really this picture of a marble in a bowl, right? I mean, there's nothing much that can happen. If you stop shaking the bowl, the marble falls at the bottom of the bowl, and that's it. But he says the main lesson of the crisis, the 2008 crisis, is that we are much closer to dark corners, situations in which the economy could badly malfunction than we thought. So in a sense, these models that I talked about try to speak about these dark corners. And finally, although I don't know whether this idea of self-organized criticality in the end is relevant or not, because as I've shown you, after our initial excitement about this, we realized that there was this other scenario where the economy is turbulent and it's nothing to do with criticality. But I still think that this idea is very important and again emphasizes this thing that we talked about this morning, the efficiency resilience trade-off. And it clearly has something to do with fragile ecologies. We spoke about this morning about this work of their time delays and buffers in transport systems, and maybe the brain is critical in that sense. And so this is a little graph explaining why this idea might be important. Is that you can imagine that you have some kind of dynamics that goes from an unstable state, and there's a region here of stability. Then it's very reasonable to believe that the dynamics in the unstable state will do something crazy. Maybe that at one point it will touch this boundary, and because below this boundary states are stable, it will stick there. So that's actually, in a sense, what Bach had in mind, is that this little picture here says it all. You start from anywhere, and then you're going to stop exactly where the system just becomes stable. And because of this scenario, it's expected that many systems fall exactly where they're fragile, precisely because of that. And actually, you can argue the other way around, which is you start by a stable system, but stability is ensured by constraints, and constraints are costly. So maybe you want to remove these constraints one after the other. And then at one point, you're going to remove enough constraints so that the system is just stable, but you're at the cliff edge this morning. Okay, so I'm going to end with a quote that I like a lot from, let me try to say that right, Willem Buiter. Very difficult for us. So I've asked a Dutch colleague to tell me how to pronounce this, because it's not at all the way I pronounced it. Anyway, so he was at Bank of England when the crisis hit in 2008, and he wrote this scathing piece, which is still very, you know, a lot of fun to read. I mean, I don't know if fun is the right word, but it's very inspiring. So it's called The Unfortunate Uselessness of Most State-of-the-Art Academic Monetary Economics. And he says, most mainstream macroeconomic theoretical innovations since the 70s have been turned out to be self-referential, inward-looking distractions at best. Research tended to be motivated by internal logic, intellectual sum capital, and aesthetic puzzles of established research programs, rather than by a powerful desire to understand how the economy works. And I think that this last sentence that I highlighted is really the crux of the matter. At least for me, I'm always struck by the fact that as physicists, we have a powerful desire to understand how the world works. And somehow this is a desire that I don't often see in economists. And I think this is a real problem because you know, if you're only interested in kind of the model because the model spits out numbers and allows you to have a career, I think there's a problem. I really think that people should be motivated by understanding how the economy works. But that's my final in a sense, he said it much better and much before me, and he's an economist, so I can take shots at it. Yes.
For the happy to, or I'm an economist there,
Good.
and I'm working on this.
Great.
But then there is, I believe, or I see some. I think it's interesting to hear because you're not an economist from
No, I'm a
background,
physicist.
right? Yeah, this is yeah. To also hear another field talking about it. But there's actually some literature emerging. Like the Carvalho, yeah.
No, that's what we were discussing
But it's
this
quite
morning.
it's quite recent.
Yeah, that's exactly the point we were discussing
Yeah,
this
yeah.
morning. That you know, this was written in 2008, and I've been
Yeah.
ranting against this since the mid-90s. So since then, things have slowly evolved, but and there are you know quite a few economists around that. But you know,
Yeah,
it's true and not true at the same time, because if you look at this paper that I referred to a lot of Asimoglu and Carvalho, 2011, I mean, this has had a huge impact, and people are still using. I mean, there's as you must know, there's a nonlinear generalization of this by Paris and Baki,
Oh yeah.
but they're still within the equilibrium framework.
Yeah.
And so for me, it's just no, there's no.
No, that's true.
It's completely equilibrium. So they go on saying that you know everything is going to be fine in Germany when gas is cut,
Yeah. No.
and they're actually happy because their prediction was more or less borne out by what happened. But I think there's something fishy about all this.
But then, or as an economist, I find it interesting that you choose because for your model you choose a Leon check model, right?
Yes.
Because then you don't assume any substitution between sectors.
Right.
So if you look at the energy crisis, as an example, you could also see that firms and sectors adapted quite well, and there's always some amount of substitution.
Yeah,
That's
sure.
important to
No,
take.
that's why I said that what is missing from this model
Yeah,
is
it's-
rewiring.
Yeah, okay, but
Rewiring
rewiring-
is a way to introduce substitution without having this strange production function that kind of you know sweeps under the rug all the process of how firms actually substitute.
Yeah, okay, but then you want rewiring on a firm level, but
Yes.
also on a bigger industry level. That you try
Well,
to
that's what you on the
substitute.
firm level.
Okay, maybe that's good.
Well, I mean, as I said, this is work in progress. But what I'm emphasizing is that this process takes time,
Yeah, of course.
and maybe in some cases it's fast, and in other cases it's slow, and it is a source of fluctuations that I don't see any intellectual argument how you could neglect them, and in these Baki-Fari extensions of, it's just not there. Just, you know, again, the economy goes back to equilibrium right away. There's a kind of, you know, hocus pocus there that I find very disturbing.
It's a religion, they pray to sink to equilibrium.
There's no bankruptcies. There's nothing at all. I mean, there's no.
No, okay, but it looks at the very big.
Yeah, but still, I mean, bankruptcies, they have to play a role somewhere. I mean, I think there are models that are completely that may be adapted to small fluctuations around equilibrium. But when there's a big fluctuation away from equilibrium, like the gas crisis, I think it's really very bold to say that it's going to work and that you can use them. And two, there's nothing like endogenous crisis that can ever happen in these models. It's just not there. And so that's as I was saying, this is for me something that is very important to think about.
It cannot really take into account large shocks.
Yeah. No. Not like exogenous or endogenous.
Before we open the